Good morning. In the last lecture, I had talked about this concept of segregation of alloying element. I had mentioned that this is very important because steel is basically an alloy, it is not a single element. Like in steel, we have along with iron, we have alloying elements like carbon, we may have manganese, we may have silicon, we may have phosphorus, silicon, sulfur, and similar other alloying elements, maybe some amount of nitrogen. So, what is important is what are the role of these alloying elements in causing segregation. We have to understand very clearly. It has impact on the quality of the final product, cast product as well as the processed product, rolled product. So, let us try to understand what we mean by segregation. So, I have mentioned that micro segregation during solidification, it is always bound to happen. When you have alloying elements, you will have micro segregation. This results in increase in concentration of an alloying element, of a particular alloying element, say we are talking of sulfur. So, initially whatever is the content of sulfur in the steel grade, and finally what you get due to segregation is different, it is going on increasing. So, what is important is the increase in concentration of the alloying element from the original value, if it is C0 in the liquid steel, that means when the solidification is starting, in that liquid steel if the concentration of a particular alloying element, say sulfur, if it is 0 C0, then due to segregation it increases, that means this to the concentration of sulfur in the last solidifying liquid, if it is called Cl. So, Cl is more than C0, this is called segregation, because the solid will release the alloying elements, alloying element will be going to the liquid. So, the liquid becomes more and more rich in the alloying element. So, the concentration of the particular element, say sulfur for example, in our example, the last solidifying liquid, if it has Cl concentration, then modified shell equation gives how this Cl, to what extent it will increase from C0 is given by this relationship. Here what are the factors? Cl is the final concentration of a particular alloying element, say if for example say sulfur in the last solidifying liquid, if this is Cl, then how is it related to the original concentration C0? It is related to the solid fraction. The more the solid fraction, more will be the segregation and higher is the value of Cl. So, there is no confusion regarding that. But what is the relationship of K? K is basically the distribution coefficient of alloying element between solid and liquid. So, K is always less than 1. So, lower is the value of K, more is the segregation, higher will be the value of Cl. So, K is important, Fs solid fraction is important, solid fraction is directly related, higher is the solid fraction, that means more it is going towards the end of solidification, Cl also increases. Small k is basically the distribution coefficient of that particular alloying element between solid and liquid. So, a concentration of that particular element in solid divided by the concentration of that particular element in liquid, this is the ratio k, and k, as I have told you, is always less than 1 because the liquid will always become rich in the solute alloying element. So, what is the value of k? Lower the value of k, you can get from this figure, lower the value of k, higher will be the value of Cl. So, this is important. Another factor here is the A. A is basically called back diffusion parameter, because what is happening, there is a difference between the two, the liquid and solid, and also from the high level of concentration in the liquid, when the particular alloying element will diffuse towards the solid. So, in the solid, what is the diffusion parameter? It is very important. So, this back diffusion parameter A is directly related to the diffusion coefficient of the particular alloying element in the solid. Solid means in the dendrite, whichever is solidifying in the form of dendrites, So, how this particular aluminium element will diffuse, so it depends on that figure, and then it depends on the local solidification time Tf. It is basically the solidification temperature interval, difference between liquidus and solidus divided by this cooling rate dt d capital T by d small t, rate of change of temperature with time. So, the dendrite arm spacing capital L is dendrite arm spacing capital L is here you find there is a capital L figure. So, that is the dendrite arm spacing. So, here L is proportional to the rate of cooling I have told earlier, and the local solidification time is depends on the solidification interval, temperature interval divided by the cooling rate. So, higher this temperature interval, the solidification time also increases, and more the solidification time, more will be the segregation. So, this is important. So, TL is the liquidus, TS is solidus. So, what is happening is the final concentration in the liquid, last solidifying liquid, is increasing from the original solidification by this relationship. This is dependent on the solid fraction. Higher is the solid fraction, higher is the concentration in the liquid, that is more is the segregation. Lower is the value of K, more is the segregation, and then higher is the value of diffusion coefficient in solid, So, this also will change the Cl value of Cl. Now, let us see how does it change. On a micro scale, partitioning of segregation of solutes from the solidifying dendrites to adjacent liquids continues throughout the casting process. That means, throughout the process of solidification, throughout the course of solidification, this partitioning of the segregation of solutes, which is the cause of segregation, it continues, because the solidifying dendrites will become less rich in the particular element, so solute elements, and the adjacent liquid will become more rich. So, this difference in concentration is called the microsegregation. Now, lower values of partition coefficient small k, as I was telling, and lower values of diffusion coefficient in solid ds, these two will result in higher enrichment, that is high values of Cl. So, consequently, the value of actual solidus TSA comes down from the equilibrium solidus. So, there are two impacts of segregation. First, the last solidifying liquid is more rich in the solutes in all the aluminium elements. So, the last portion which is getting solidified is more rich in solutes. So, its concentration all the aluminium elements in steel in the last portion which is getting solidified is much higher compared to the original concentration, or the initial portion of the solid which is solidifying, that is much leaner, and the last portion which is solidifying is having more concentration, that means it is richer in all aluminium elements. So, first is this concentration of the last solid is very high, quite rich, the last portion of solid which is getting solidified, number one. Number two, the actual solidus which is known as TSA. TS is solidus, TSE is the equilibrium solidus, TSA is the actual solidus. So, the actual solidus also comes down because of the segregation. So, higher is the segregation, more will be the Cl, that is the last concentration in the liquid which is getting solidified. Similarly, the solidus, actual solidus is also decreasing. So, because of this range of solidification, which is nothing but the difference between the liquidus and the actual solidus, this also is increases, and if this increases, I have told you what is going to happen. The actual depth of Massey zone, solid plus liquid, is more, and the actual thickness of the solid shell during solidification is less. So, the actual thickness of solid shell is narrow and the depth of marshy zone is more. So, segregation is causing these 2-3 important consequences which have impact on the will have impact on the quality of the cast. First, the last portion of the solid which is forming, that is the last portion which is getting solidified, is very rich in alloying elements compared to the earlier portion of the solid. So, the central portion of a cast material is always more rich in alloying elements, more rich in solutes, number 1. Because of segregation, which is a important consequence of solidification, there will be segregation. All alloying elements will segregate, because for all alloying elements the partition coefficient K is less than 1. Now, it is a question of which value is lower. The lower value of small k and lower value of diffusion coefficient in solid ds, they will increase enrichment Cl, that means more segregation, and more is the segregation, lower will be the actual solidus, and lower is the actual solidus, more will be the actual solidification range, and because of this the depth of marshy zone increases at the cost of the solid shell during solidification. Depth of marshy zone is increasing, solid shell is becoming less. This is a consequence of segregation. So, whatever alloying elements cause more segregation, which I will come just subsequent to this, which alloying elements will cause more segregation. The results are the last portion of solid will be very rich in those elements, number 1. The marshy zone will be quite broad, actual solid shell will be quite narrow. So, this has lot of consequences on the quality of the cast product. Now, why we tell that phosphorus and sulfur are very deleterious? These are harmful for a cast product. The reasons I have mentioned, some of the factors which are responsible. I have mentioned that partition coefficient between solid and liquid, small k, is always less than 1 for all alloying elements during solidification. Now, these k values are not equal for all alloying elements. Different alloying elements have different k values, number 1. Number 2, k values are also different for the solid which is forming from liquid. If it is delta ferrite, you have some k values. If it is austenite, that means gamma, you have some k values. Now, wherever k values are smaller, I have mentioned several times that very small k will cause very high amount of segregation. So, look at the different values of k for different alloying elements. So, manganese, silicon, what are the values of k? It is around 0.7, and look at the values of phosphorus and sulfur in delta and gamma. In delta 0.23 phosphorus, gamma solidification is 0.13, still lower. Sulfur 0.05, compared to phosphorus, sulfur segregation is more, gamma 0.035. So, there are 2 observations from here. First, phosphorus and sulfur will segregate more compared to alloying elements manganese and silicon. Why? Because k values are smaller. I have mentioned here that smaller values of partition coefficient k will give rise to higher enrichment, that means Cl. From this modified shell equation you can see Cl will be higher once this k becomes lower, k to the -1. So, this is negative to the power. So, k, smaller the value of k, higher is the value of Cl, higher is the value of enrichment. Then another factor, back diffusion parameter A, it consists of diffusion parameter in the solid ds. So, lower is the value of ds, lower is the value of A, and Cl also will increase. So, 2 low values of k, small k, and ds will increase Cl, that is enrichment. Lower values of partition coefficient small k and lower value of diffusion coefficient in solid ds for an alloying element result in higher enrichment Cl. Higher is the enrichment, I have told you, actual solidus comes down from the equilibrium solidus. Because of this, the actual temperature range of solidification, what is that? The temperature difference between liquidus and the actual solidus. This temperature interval, the range of solidification also increases because of segregation. So, lower is the value of K, lower is the value of ds, higher is this range, higher is the segregation. So, the depth of marshy zone also will be more, actual thickness of solid shell also will be less. So, now if you look at the values of phosphorus and sulfur, these values are much less compared to manganese silicon, number 1. Number 2, in gamma solidification, these values are still less. So, this partition coefficient between solid and liquid, K is less than 1 for all alloying elements, but for alloying elements like phosphorus and sulfur, these values are much lower compared to those for manganese and silicon, the common alloying elements in steel. Number 1. Number 2, these low values of K for phosphorus, sulfur in case of gamma solidification, you look at these values is still lower compared to delta values. So, phosphorus and sulfur K values in case of gamma solidification is relatively much lower. So, what is going to happen? What are the consequences? These two elements will give rise to high level of microsegregation, and consequently the actual solidus becomes much lower compared to the equilibrium solidus. So, what are the consequences? The consequences are the microsegregation level caused by phosphorus, sulfur when in case of gamma solidification is much more. So, high manganese by sulfur is necessary, otherwise what is going to happen? If you have sulfur, it will react with iron, so it will cause formation of iron sulfide which has low alloying element. That is the reason why sulfur segregation is bad for quality of steel, because the actual solidus becomes much lower. Now, if you have high amount of manganese in the steel, if the ratio of manganese by sulfur is more than 25, then what is going to happen? There will be formation of manganese sulfide and not iron sulfide. Manganese sulfide, temperature, melting temperature is more compared to iron sulfide. So, the deleterious effect of sulfur, like why it is deleterious? Because it forms low melting iron sulfide. So, if you have higher amount of manganese by sulfur ratio, then manganese sulfide will form and not iron sulfide, and in this process the deleterious effect of sulfur will be taken care of to a large extent. But unfortunately for phosphorus, there is no such element which can take care of this element phosphorus. So, what happens in presence of phosphorus? Iron phosphide forms Fe3P. This iron phosphide has low melting point. So, it causes incipient fusion, it causes the actual solidus temperature to get down. So, that is the reason for phosphorus to behave in this fashion. So, the deleterious effects of sulfur can be taken care of by using manganese, but the effect of phosphorus, the deleterious effect of phosphorus, the harmful effect of phosphorus cannot be taken care of by any other alloying element in liquid in steel. So, phosphorus has to be kept under control so that its deleterious effect is not much. Now, another important thing is this low melting liquid which causes central segregation. That means, at the last stage whatever liquid remains during solidification, as I have told you, it is very rich in alloying elements, all alloying elements. Relatively it is very rich in all alloying elements in steel because of segregation. Now, some alloying elements will segregate more like phosphorus, sulfur, some alloying elements manganese, silicon, they will segregate less. So, we have to be more careful about phosphorus and sulfur in steel. And I have also mentioned that the deleterious effect, the harmful effect of sulfur can be taken care of to a certain extent by using higher manganese in steel. So, say if you have 0.2 sulfur in steel, what should be the minimum manganese percentage? 0.2 into 25, that means 0.5. So, normally we must have 0.5% manganese, so that the deleterious effect of 0.02% sulfur is taken care of to a large extent by manganese. So, this is the role of manganese is very important here, but since there is no such element which can take care of the harmful effect of phosphorus. So, phosphorus has to be controlled to very low level, so that this harmful effect of segregation effect of phosphorus is taken care of by keeping the value of phosphorus to lower level. This is very important.